And so for our last talk of this first afternoon session, we're going to go back to the physical world. And it's my pleasure to introduce Peter von Nieuwenhuizen, who's Distinguished Professor of Physics at Stony Brook University. He studies quantum field theory with applications in supergravity, supersymmetry, and string theory. And as we heard earlier, he shares this year's special Breakthrough Prize in Fundamental Physics for his work on the theory of supergravity. The title of his talk is The Future of Supergravity, Dream or Reality? It's a very exciting question.
A month ago, I was lecturing at Stony Brook for graduate students, and when I reached the subject of supergravity, I explained how beautiful it is, how interesting. But then one student asked, "Did you write any articles on supergravity?" I was a little bit taken aback, but the students around him pounced on him and said, "Don't you know, he just won the Breakthrough Prize, and he got $1 million for the first article." I wanted to go on, but he asked somewhat incredulously, "Did you really get $1 million for one article?" I told him that I've written about 350 articles, and that therefore I got $3,000 per article. And he seemed to conclude that physics can be a somewhat lucrative business. And then finally, I wanted to go on, but he asked the last question. And the last question was it obvious to write that article? Well, it was not obvious then, but now with hindsight it is obvious. And what I'd like to do now is explain to you the basic principles of supergravity in such a way that if you came here and you didn't understand it, you leave and you hopefully understand it. So what is supergravity? Supergravity is Einstein's theory of gravity, general relativity, GR, with an extra symmetry between the two kinds of particles in our universe, bosons and fermions. I expect you not to understand a word of this. I'm going to explain it. What were or are its aims? On the one hand, theoretical physics, basic theoretical physics, is based on two pillars, quantum mechanics and general relativity. Einstein's theory could not unify these two. Our theory is an extension of Einstein's theory which marries the two. General relativity, long distances, quantum mechanics, short distances together. The other aim was and is unification of all particles and all forces. Now let me first briefly mention something about unification of particles. Every particle spins around its axis, but the amount of spin is quantized. You have spin 0 particles, these are the Higgs bosons which have been found. Spin 1/2 particles, electrons, neutrinos. Spin 1 particles, the photon, but also the electromagnetic, the gauge fields for the strong interactions, and the Z and the W bosons which were found in CERN for the radioactivity. And at spin 2 you have gravitons, which are needed to get the general theory of general relativity of Einstein. But there was always, as Dan Friedman already explained, this gaping hole of spin 3/2. Now, the spin 0, 1/2, and 1 have been unified in something called the Standard Model, which is extremely successful, but it doesn't contain gravity. Supergravity unifies all spins from 0 up to 2. But there are also particles which have higher spin, 5, 1/2, 3, and they have very heavy masses. And string theory unifies all these particles, including the very heavy ones. Now, spin 3/2 is the glue between general relativity and the Standard Model. You may wonder what these asterisks in green are. These are the breakthrough prizes. You can see that string theory in soccer terms leads against supergravity something like 9-1. Maybe that can change. So the contents of my talk are now, I'm going to explain to you what is general relativity, and I think I can do it in such a way that if you didn't understand what it is, you learn what is the basic essence, in my opinion. Then I will tell you about bosons and fermions, but then I will tell you what it means to have a symmetry between particles. And then I will show you two aspects where supergravity does better than Einstein's theory of general relativity. I'll show you that quantum corrections are better, and I'll also show you that if you go to higher dimensions, you can unify theories. And I will end with reflections on the state of physics today, my wishes for the future, and also there may be some young people in the audience who want to enter science, so I have some advice for young scientists. So let me explain first what general relativity is. Newton said that two masses attract each other. You see there a planet going around the sun, and the orbits of planets are exact ellipses. This was known since Newton. Einstein said two things. E is mc squared. I'm sure you have heard about it. So energy is mass. And secondly, in 1917 or 1915, he said, energies attract each other. Not masses, but energies. Now, if you have a planet and the sun, there's a gravitational field between the two, and that gravitational field has energy. But Einstein said energy is mass. So between the planet and the sun, there's also mass density. Now, a planet, according to Newton, feels all mass. Not only the mass of the sun, but the planet also feels the mass which sits between the sun and the planet, that mass density due to the gravitational field. And that extra mass leads to an extra force, and that extra force makes the elliptical orbit precess forward, as you can see in that illustration. Now, for Mercury, the effect is exceedingly small. It's 1/50th of the diameter of the sun per century, but the effect has been measured and it completely agrees with Einstein's prediction. So the final message I have is, if you take special relativity, mc squared, E is mc squared, and you take Newton's theory and you reason logically, you get general relativity. Now, what are fermions and bosons? They're the building blocks of our universe. They're named after Enrico Fermi, an Italian physicist, and Bose, an Indian physicist. Supergravity makes a statement that for every building block, there must exist a superpartner, for everyone. So, for example, the fermions we know are quarks, electrons, neutrinos, positrons, which are antiparticles of electrons, and they have partners. But the partners of fermions are bosons, and they have funny names. They're called squarks, S for superpartner, selectrons, and so on. We also have bosons in our world, which we have seen. Photons, quanta of the electromagnetic field. Gravitons, quanta of the gravitational field. Gluons, quanta of the nuclear force. WZ bosons, quanta of radioactivity. And for those bosons, there are also partners. They are fermions this time, and they have names like photinos, gravitinos, gluinos, and so on. Now, in the first column, all these particles have been observed, and many prizes have been given for them. In the second column, we have all the superpartners. So there's an enormous number of particles to be discovered, but you've heard already the sad news. Up to now, not a single of these superpartners has been discovered. I will address that question. Now, this doubling of particles is not new in the history of physics. In 1928, Paul Dirac claimed that for every particle there's an antiparticle. For a neutrino, there's an antineutrino. For an electron, there's an anti-electron, which is called positron. And sometimes particles are their own antiparticles. Photons are antiparticle photons, and gluons, antiparticle gluons. And gravitons, I could add, antiparticle gravitons. Now, Dirac got antiparticles by taking the square root of the wave operator of Maxwell. So in this single equation I'm going to show, the square root of the Maxwell operator, which is on the left-hand side, is equal to, and on the right-hand side you get single derivatives, ddx, dy, ddz, ddt, multiplied by objects which Dirac identified as matrices. So square roots give antiparticles. Supergravity claims that if you take the square root of general relativity, you get supergravity. So same idea as Dirac, and also doubling of particles. Now I'm going to explain what a symmetry is. Let me begin with something very simple. If I have a cube and I rotate it 90 degrees, the surface looks the same. You cannot tell whether the cube has been rotated or not. If I take a sphere, I can rotate it around a vertical axis or a horizontal axis, but you cannot tell, if you look at the surface, if it's rotated or not. In the sphere, I can only rotate over finite discrete amounts. In a sphere, I can continuously rotate, but you won't see a difference. So a symmetry means that you cannot tell whether an object is rotated or not. The surface is the same. Now, a local symmetry means that different parts of the sphere you rotate in different amounts, so you deform the sphere. But it is still true that if you look at the surface, you cannot tell if it was locally rotated or not. But local symmetries will lead in general to the word gauge theories, which Dan Friedman explained, and gauge fields. So the gauge field associated with general relativity are the graviton fields, and gauge fields of local supersymmetry, or supergravity, are gravitinos, as Dan already explained. Now, I'll work this out a little bit. Suppose you see a boson as a hemisphere. For example, I take as hemisphere the graviton, and if I take a vertical axis and I rotate that hemisphere, you won't see a difference of the surface. That symmetry is what Einstein's theory of general relativity is. I could write complicated equations down, but it is really in symmetry, and you rotate something and it doesn't change. But if I take a horizontal axis and I rotate that hemisphere, it looks different. So that's not in symmetry. If I now look at another particle, the gravitino, with a green other hemisphere, again, if I rotate around a vertical axis, you will not see a difference in the surface, so that is in symmetry. That is the same symmetry as Einstein found in 1915. But if I rotate around a vertical axis, then you will see a difference if it's rotated or not, so that is not in symmetry. So now here comes the simple point of supergravity. If I bring these two particles together, they form a sphere. But in sphere, if I rotate around a vertical axis, you won't see that the surface has changed. That is Einstein's symmetry. But if you now take a horizontal axis and you rotate, you also won't see that the surface of the sphere has changed. And that is the new symmetry for which we got the breakthrough prize, supergravity symmetry. Now the change in a boson is a fermion. If I change the sphere, rotate around the vertical axis, the red upper half recedes a little bit and the green upper half comes up. So there's a change, what you see in red and green. And the change in the red is proportional to the green times an angle. And similarly, the change in the green is proportional to the red times an angle. But what is new here is the mathematics. The angles over which you rotate and the fermions are described by a new kind of numbers which were invented in the 1800s. And they have the property that A times B is not equal to B times A, but minus B times A. This is essential for these new ideas. Will supergravity turn out to be true? So I'm going to show you two applications where you can see that the theory of supergravity does better than the theory of Einstein gravity. The first has to do with quantum corrections. And all I can tell you is this. The quantum corrections are very complicated, but you can write them in pictures called Feynman diagrams. And these calculations usually give results which are of the form 1 divided by 0. And as probably all of you understand, that is infinity and therefore a terrible thing to happen. So here you see on the left, when I wrote the letter ME, all the calculations or Feynman diagrams you can do if you take the theories of Maxwell and of Einstein, but not yet supergravity, only Maxwell and Einstein, and you do all the loop calculations or the quantum calculations. And indeed, you get this horrible 1 over 0 multiplied by an integer, which is a fractional number, which is a rational number, 137 over 60. So that demonstrates that Einstein's theory is not a good theory to unify quantum gravity with general relativity. But these new pictures, that is what we invented. They have to be added to what Einstein and Maxwell did. And if you add it all up, there's a miracle happening. And when it happened, my heart stopped beating for a moment. They add up to 0. Now, 0 for a theorist is the most beautiful number. So this showed that, yes, supergravity is a better theory than Einstein gravity in the quantum domain. Now, there have been also 2-loop, 3-loop, 7-loop, and Dan mentioned that already in a particular model. But other models exist where supergravity is not finite. And in string theory, all loops are finite. The verdict is out if supergravity by itself will be all finite, or that one has to go to string theory for all loop finiteness. Let me now show another application of supergravity. Namely, if you go to higher dimensions, you can unify theories. Now, let me begin by reminding you that Newton said that what is called the Laplace operator, that is the difficult operator in the first line on the left-hand side, is equal to proportional to the mass m on the right-hand side. That is what Newton said. Now, in 1912, there was a Finnish physicist who didn't get much credit. His name was Nordström, and he did a natural extension of Newton's theory. He replaced the Laplace operator by the D'Alembert, so he added that term d2 dt squared in the equation. And that is what Einstein had told physicists in 1905. So Nordström, 1912, 7 years later, just applied what Einstein had told him. It's called special relativity. And instead of the mass, he wrote a relativistic mass, which is Tmm, T mu mu. So that is what Nordström did. But then 1 year later, he had an absolute fabulous idea. He had realized that people could unify space and time into a 4-dimensional representation. So he said, let's look in higher dimensions, 5 dimensions, and look at Maxwell theory in 5 dimensions. It has 5 components on the left-hand side. But then the first 4 components are the Maxwell theory in 4 dimensions. And the last component, he said, that is my field phi for gravity. So he showed in 5 dimensions Maxwell theory gives Maxwell theory in 4 dimensions and Nordström's gravity. But Einstein showed that it was completely wrong because his theory did not predict light deflection at the sun. So it seemed that the whole idea was wrong. But then in 1921, Theodore Kaluza, a mathematician, and Oscar Klein, a physicist, applied the same idea of Nordström, but this time starting with Einstein gravity in 5 dimensions. So in this equation on the left-hand side, you see the 5 by 5 matrix for the gravitational field. And on the right-hand side, you divide that 5 by 5 matrix in a 4 by 4 blocks, g mu nu of x, that is Einstein gravity, a mu of x, that is Maxwell theory, and then there is a strange scalar field. But notice, that scalar field cannot be gravity because gravity is now g mu nu of x, Einstein theory. So this field, phi of x, is in modulus, and we heard from Alex all about moduli, so that is a new interpretation. So this was how higher dimensions, namely 5 dimensions, explain theories in 4 dimensions. Now in supergravity, you can go as high as 11 dimensions. But then you get more complicated theories if you go from 11 dimensions to 4 dimensions. So if you would have gone from 11 dimensions in the early days to 4 dimensions, one would have discovered what is called Yang-Mills theory. It is an extension of Maxwell theory, which explains the standard model. Yang-Mills theory is the great discovery. But It was discovered by my colleague at Stony Brook, Professor Frank Yang and Bob Mills, in 1954, having nothing to do with higher dimensions of gravity in a complete different way. So that success cannot be claimed by going to higher dimensions. Now, there are a lot of people working in this field of higher dimensions, and some of these people say the following: the only way to do Kaluza-Klein is through supergravity, and the only way to do supergravity is through Kaluza-Klein. Now, in 1985, a particular supergravity theory, its name is 2B supergravity, in 10 dimensions, was reduced down not to 4 dimensions, but to 5 dimensions. And then a miracle happened. Maldacena, who is not here today, realized that a theory in 5 dimensions can explain, a supergravity theory in 5 dimensions can explain non-gravity theories in 4 dimensions. This is the ADS-CFT correspondence, which Dan also mentioned. So that was how higher dimensions unify theories. So what directions is physics headed into? You see, we're in a very situation which is even not known by the introduction this morning, when it was said in all fields we have enormous explosion. This is not true in particle physics, experimental physics. We're in a very strange situation. All experiments agree with the standard model of non-gravitational interactions. All experiments have been done agree to many decimals even. And some people say this is a horrible time for physics. It's stagnant. I disagree. It's a golden time for theorists, because now you have the freedom to go outside the box of experiment. And indeed, we have a flood of new ideas, of which supergravity is one. Now, obviously, a lot of that new stuff is worthless, and some stuff is very good. So how do we figure out what is right or wrong? Instead of physical normal experiments, what we now can do is thought experiments, things Einstein initiated. And in particular, the thought experiments we do today is go to higher dimensions and try to see if certain theories are inconsistent. And indeed, most of the new theories can be ruled out this way. Now, I have worked 50 years in this field, and I must say most of my work, and of most people, considers discoveries. We work in a very solid framework of basic principles. Everything is in agreement with everything. All basic laws are very clear. But sometimes there are people who go outside this framework, do something totally unexpected. I can only think of 2 people. One was Dirac, whom I mentioned, and I could tell you some anecdotes if they're interested afterwards. And the other was Maldacena, who had that ADS-CFT idea. So now we are coming in a new era in physics, where we no longer look at particular models like the standard model, but we are having a new framework, in my opinion. Supergravity, I would postulate, is a framework. It can be applied in particle physics, it can be applied in cosmology, but I believe it can also be applied in condensed matter physics, and even on the long run in biology. So no longer particular models, but frameworks and classes of theories. And it may very well be that in the future, breakthrough prizes are for framework of new ideas. So let me now first come to my wish list for the future. The first thing is my dream that one morning I waken up, I take my New York Times from the driveway, and front page news is, a superpartner has been discovered. Now, as you have heard, in CERN, no superpartners have been discovered. In Fermilab in Chicago, none have been discovered. But maybe it may happen in the new accelerator, which is perhaps being built in China. I think we reach the energy range where it can happen. Another thing I would like to mention here is the origin of the cosmological constant. Most people say that nobody knows, and I will tell you, but I will immediately disqualify it, that I believe I know what it is. It is 0-point energies of a supergravity theory at the Planck scale in a curved universe. So what do I mean by that? If you have a flat universe, then you have equal number of bosons and fermions. That's the symmetry between both. Each particle has a 0-point energy. The 0-point energy of a boson is positive and fermion is negative, but equal number of particles and equal absolute values of the 0-point energy, they completely cancel. But in a curved universe, the bosonic 0-point energies get a little bit up, but the fermion zero a little bit less down, and now the sum no longer cancels, but there's a tiny bit left over. So I predict that the cosmological constant is proportional to 1 over the radius of the universe. Now, I have talked with colleagues about that, and they think this is completely ridiculously wrong. And the only argument I have, I can tell you this, is that there's a saying, I'll say it in German and I'll explain it. Sie sind alt genug, sich eine Dummheit leisten zu können. You are old enough to afford a stupidity. And there is some little nice historical story, so again, in the question period, I can say more about it. Dark matter, it would be wonderful if it's gravitinos or superpartners, as Dan already said. So that's a wish list for me too. But even if none of these things will happen, supergravity will remain. First, it solves unsolvable problems in mathematics, and the reason is that supergravity takes also the square root of problems in mathematics which were considered unsolvable. But the square root of these problems can be solved. The chairman of the Breakthrough Committee this year was Edward Witten, and he made an enormous number of discoveries in that direction. And also, a supergravity can just clarify the structure of other theories like the Standard Model. The reason is that calculations in supergravity are so much easier to compute with. Remember, I showed you that these 1 over 0 terms cancel in supergravity. However, I have to say that Schwinger once told me, and others, that the future lies ahead. And that's, I think, a wise lesson we shouldn't forget. Things always turn out different from the way you expect them to be. So let me close with advice for some aspiring scientists. First, do what you like. Do not do what you don't like. Play, as Dirac said, he likes to play. I would say listen politely to experts and then forget what he said and go your own way. Second, explain to friends what you don't understand. As a professor, I usually explain to students what I don't understand, and while I explain it, I understand a few more things, and the students understand a lot more, and together we progress. Become an expert in one thing, at least one thing, and then don't let go. In particle physics, there's an enormous competition, and eventually you will be overtaken by a horde of competitors. But if you keep running in the beginning, you have a time that you stay ahead of the crowd, and that's what Dan, Sergio, and I did. And then that's the time you should not let go. You should not take holidays in that time. And when you're overtaken, take all the holidays you like. Learn to calculate. My education was in Europe, where I got a beautiful education, but it was based on ideas and philosophy. And then I've been 50 years almost now in the United States. There the emphasis is on calculations. I think the best is to combine both. But my advice is, if you don't learn to compute, you will never achieve anything in physics. Calculations are crucial. So this is now the end of my talk. And let me quote Goethe. That's why I have given into magic to know what makes the world tick. I could say it in German, but I'll say it in English. Science is a rock of truth in a sea of fake news. Science is culture. It opens windows to see what makes the world tick. Science is the only ideology that is self-correcting. It is needed for society. The future is at stake. Thank you.
In the interest of time, we will take one question before the break, but then we can hopefully talk more about this really inspirational talk. Right here.
Who made the statement, Sie sind alt genug?
Ah, yeah, that's a nice term. There were two students in Leiden in the 1920s, and they invented the concept of spin. And they wrote an article about it. Their names were Goudsmit and Uhlenbeck. And their professor was Ehrenfest, who was mentioned in Alex's talk. And he went to the famous Lawrence, who was living a little bit nearby. And the students had sent the article to a journal, but then Ehrenfest showed Lawrence what his students had done, and Lawrence said it's completely wrong. And so the professor went back to the students and said, it's bad news, but your article is completely wrong. And the students said, oh, this is a disaster, because now our careers are ruined. But then Ehrenfest said the famous word, Sie sind jung genug, sich eine Dummheit leisten zu können. You are young enough to stay a stupidity. And I'm old enough. Thank you.